Dear students, I welcome you all to this digital electronics tutorial series. In this video, we will learn about the duality principle. First of all, let me explain you what is the duality principle. The duality principle states that every valid Boolean expression remains valid if the operators and identity elements are interchanged as follows. We have to follow some steps so that given expression remains valid. So first point will be, let me write down here, 1 will be replaced with 0. Okay, I am showing here both way. Okay, 0 will be replaced with 1, 1 will be replaced with 0. Okay, that means in the given Boolean expression, we have to replace the ones with zeros and zeros with ones in the given, suppose, truth table. Next step, second step, first of all, let me write down the steps. Second step, and logic, and we represent with a dot. Okay, and will be replaced with OR logic. So here let me write down OR. So this is a operator. So operator we can change. OR is represented with a plus symbol. Okay, so this is the second point. Third point we have to remember is keep the variable as it is. So let me write down here. This is the third point. These are the three important steps you have to follow while finding out the dual of a given expression. First of all, we have to see that when a positive logic we have to replace with a negative logic. Then the dual theorem or duality principle will be applied. Next, in the case of, suppose if we are given with a given circuit with a NPN transistor, then that NPN transistor will be replaced with PNP transistor. I hope you are familiar with PNP and NPN transistor, or we can say MOS also. Third point will be when we have a NMOS circuit, then it will be replaced with PMOS circuit. Then the duality principle will be applied, or then we will find out the dual of a given expression. Let us consider some given voltage, then we will see the positive and the negative logic. Suppose we have A and B, these are the input variables. Suppose output variable is Y. Okay, so input variable A might have, suppose, 0 volt. Then suppose B is also 0 volt. We may have here, we will be having 4 combinations. So 0 volt, 5 volt. 5 volt will represent the one value. I am considering here the default assumption. Okay, next we have 5 volt, 0 volt. 0 volt in the B input. Next we have 5 volt and 5 volt. Okay, both the input are 5 volt, 5 volt. Suppose these are the given 4 input combinations, and let us assume the output Y is 0 volt for both the input 0 0. Let us consider the AND operation. Then what will happen? 0 volt and 5 volt, what will happen? 0 volt, because it is a AND operation. So in every case you need not to consider this AND operation. Okay, now for the third input combination, we have 5 volt and 0 volt. We will be having 0 volt. Here this is the capital V that is representing the voltage. Okay, next we have 5 volt and 5 volt. What will happen? We will be having 5 volt at the output. Suppose this is the given functions. So suppose these are the input and output voltages. Now let us consider positive and the negative logic. So if we consider positive logic, so what will happen? We have to write 1 and 0. So all the positive voltages, that is the 5 volt will be represented by 1 value, and the 0 volt will be represented by 0 value. Okay, now let us consider the positive logic. So A and B, these are the input and Y is the output. So what will happen? So 0 volt means 0 0, output is also 0, so 0. Okay, next we have 0 1. Why I am writing 1? This is a plus 5 volt, means it is the logic 1. So what will happen? Output is also 0. 0 volt means the logic 0. Okay, next we have 1 0. So output is 0. So I am deriving this table from this one, given voltages. Okay, I am deriving this truth table. Okay, next we have 1 1. So 1 and 1, this is the logic 1. Okay, next we have output is also 1. Okay, this is applicable for the positive logic. So in the case of negative logic, what will happen? In the case of negative logic, let me write down A, B, these are the input and Y is the output. Logic 0 will be representing the negative voltage. Next, so what will be having 0 and 5? This means 1, 0. 0 means here for the negative logic it will be 1 and 0 and output is 1. Next we have 0, 1 and output is 1. Next we have 0, 0, output is 0. So this is the voltage table. Next we have, this is on the left hand side we have the positive logic, on the right hand side we have the negative logic. Okay, I hope up to this point you are clear. So let me explain you with a given circuit, then you will understand, and then we'll go to our different values, that means the different operators. We may have a buffer, we may have a NOT gate, we may have a NAND gate. What will happen in the case of duality? Okay, we will consider examples as well and we will prove it. Okay, next, first of all, what will happen? Suppose if you are given with a circuit, suppose we have a resistance here. Next we have a suppose NPN transistor, because this is a NPN transistor expression. We have an input A here, and suppose next we have another NPN transistor. Suppose we have a ground here. Okay, next, so what will be happen? So what will happen here? This is the input B. Suppose we are taking the output from here. This is the F, and we have a VCC, that is the collector to collector voltage. This is the voltage here applied here. Now F is equal to A B bar. Why A B bar? Suppose this is the given expression. So what will happen? Now you have to find out the dual of this given circuit. Okay, what will happen? Positive logic will be replaced by negative logic. So we have to apply here minus VCC. First change will be here. Okay, next we have a resistance. Then what we'll have to do? NPN transistor will be replaced with PNP transistor. Okay, so let me draw here. So here we'll be having a PNP transistor. Next we have another NPN transistor. So what will happen? Next we have another transistor. What will happen? This NPN transistor will also be replaced by a PNP transistor. Okay, so this is input B, this is input A. Okay, so these are the inputs. Now we have to take the output from here. F, in the superscript we are writing D. This D means here it is the dual of the given function. So A into B, this is the given expression A B bar. Okay, so what will happen if we find out dual? It will be coming like this, A plus B whole bar. So I will consider various example in this video itself, so I am not explaining more in this video. So what we have to do, we have to, first of all, positive logic will be replaced by negative logic, then we will be applying the dual theorem or duality principle. Next, third step will be, if we have NMOS, then what we'll have to do, we have to replace with a PMOS. Here in this case it is not applicable. Okay, in some other cases it might be applicable. Now let us consider different examples one by one. Suppose example number 1. Suppose we have a given function f equal to a. We have only one variable. Okay, so this is called as the buffer. Okay, we have a buffer here. Okay, next, if we find out the dual of the given buffer, what will happen? This will remain as it is, because we do not have any kind of operator to interchange. Okay, because let me show you here, these are the rules. 1 will be replaced with 0, an operation will be replaced with or operation, and keep the variable as it is. Here we do not have any kind of operation, so we have to keep the variables as it is. So here f and dual of the given function, they are exactly same. So we can write here, for single variable, if there is no operator, then we can write f equal to fd. Second is the NOT operation. If we have the given function is a complement, so this is a NOT operation. So what will happen if we find out the dual of the given function? What will happen? this will be also remain as it is, because we have to keep the variable as it is. If there is some kind of information, or if there is some kind of operation or operator is present, then we have to do the interchange of operator, that is and will be replaced with or will be replaced with and. Okay, this is also second case. Here we have the not operation. In the third example, let us consider f equal to a b. So what is the meaning here? This is the and operation. This is the AND operation. If we find out the dual of this given function, what will happen? Here we have a AND operation, dot is there. So we have to replace the AND operation with OR operation. Let us read the rules again. These are the steps. Okay, steps involved or procedure for finding the dual of a given expression. So we are replacing the AND operation with OR operation. We are keeping the variable as it is. OR operation. So what do we understand from here? AND operation is reversible with OR operation in the case of dual expression. Okay, so here we have found out this one. Now let us consider the fourth example. In the fourth example, we have the OR operation. Suppose f equal to a plus b. Okay, f equal to a plus b. This is the OR operation. I hope you are getting this point. Now let us find out the dual of the given function. Operands will remain as it is, the variables will remain as it is. So a will be remaining as it is, b will be remaining as it is. Here we have a plus, it will be replaced with a dot. That means now it is becoming a AND operation. Okay, that means this is again valid, or is represented or can be replaced with AND operation. Okay, this is the fourth example. Now let us go to our fifth type. So in the fifth type, let us consider a NAND operation. Suppose f equal to a b whole bar. So this is a NAND operation, that is the complement of the AND operation. Okay, now we can write it as ab whole bar. That means using De Morgan's theorem, we can write it as a bar plus b bar. I hope you are clear up to here. So this is a suppose NAND operation. Let me write down here. This is a given NAND operation. If we find out the dual of the given expression f of d fd equal to, so what will happen? This is the given expression now. So from here we can write a bar will remain as it is. This plus will be replaced by dot a bar b bar. This b bar will remain as it is. So this can be again rewritten as using De Morgan's theorem a plus b whole bar. Okay, a plus b whole bar equal to a bar dot b bar. This is the De Morgan's theorem. Okay, so this is the NOR operation. So what we understand from here, that NAND gate and NOR gate are replaced by one another. Okay, in the case of duality principle, NAND and NOR gates are interchangeable. In the case of here, we can see here we have seen for two variables. Okay, now let us go to our sixth type. In the sixth case, we will consider NOR operation first. F equal to a plus b whole bar. Suppose this is the given expression. So what will happen? This is the NOR operation. Now, if we find out the dual of the given expression, what will happen? So let me write down here a plus b whole bar means a bar dot b bar. So this is the NOR operation. Now, a bar will remain as it is. This dot will be replaced by plus, that is the OR operation, and will be replaced by OR operation, so it will remain as it is. So a bar plus b bar. So a bar plus b bar we have already seen. A bar plus b bar means ab whole bar using De Morgan's theorem, ab whole bar. So this ab whole bar means this is the NAND operation. So we have again proved this part also. This part is valid for the opposite case. Okay, now let us go to our seventh type. So what we'll do here, in the seventh type, we will consider the EXOR operation. So if we have a given expression a EXOR b, So this is the given expression. We have to find out the dual of this given expression. So if we break this XOR operation, what will have? A bar B plus A B bar. Okay, this is the given operation. Now if we want to find out the dual of the given function, we have to follow the steps. Okay, so A bar and B, this will remain as it is, but here we have a dot. This dot will be replaced with a plus. That means this AND operation will be replaced by OR operation. So here we can write A bar plus B. Operands will remain as it is. Okay, here we have a plus, so this plus will be replaced by a dot. Okay, next we have A, here also we have a dot, so this will be replaced by OR operation, A plus B bar. Okay, I hope you are clear up to here. Next, what we'll do here, in this expression we will apply the transposition theorem. So using transposition theorem, what will happen? We have two variables, we have one of them is in complemented form, this another is also in complemented form. So we will be multiplying by nearby terms and we will be multiplying the far terms. So what will happen here, if we multiply here and we have to remove this dot with a plus, this is the transposition theorem. I hope you have already watched my video on transposition theorem. So what we can write, we can write A bar will be multiplied with this B bar. So A bar dot B bar, again this multiplication will be converted to a addition or OR operation. So what will happen, this nearby term B multiplied with A, so we can write A B. Okay, this is using transposition theorem. So what is the expression here? So A XNOR B, this is the expression for A XNOR B. So we can write the dual of the XOR operation is the XNOR operation. Okay, so we can write XOR operation, the dual will be XNOR operation for two variables. This is applicable for two variables. That is, the dual of a given XOR operation of two variables will be the XNOR operation of the two variables. Okay, now let us consider the opposite case. So let me write down here, this is the 8th number case. So here we have F equal to A XNOR B. So let us expand this. A XNOR B, we can expand it as A bar B bar plus A B. Okay, so this is the expansion of the XNOR operation. Now we can find out the dual of the given function f d equal to A bar will remain as it is plus B bar. Why? We are replacing this dot with a plus and this plus will be replaced with a dot. So it will be A plus B. Okay, up to here you are clear. Now again, if we apply here the transposition theorem, what will happen? This will be multiplied and this will be multiplied. Okay, so what will happen? Let me write down here. A bar will be multiplied with this B, A bar B plus A B bar. A B bar. This is nothing but the transposition theorem. So this is nothing but this is the XOR operation. A XOR B. Again, this is proved. Okay, XOR and XNOR are the dual of one another. So these are the expressions. So we have considered 8 different cases, and for those cases we have found out the dual of the given expression. For the buffer case, it remains as it is. Okay, for the NOT case, it also remain as it is. The given function and the dual of the given function, they are actually self-dual, we can say like that. Next we have AND operation and OR operations are dual to one another. Okay, next in the fourth case, OR is also, we can replace it. Okay, NAND operation and NOR operation, they are dual to one another. Okay, next we have XOR operation for two variables. Here I am mentioning that it is applicable for two variables. XOR operation and XNOR operation are dual to one another. Okay, this is the 7th case, and the 8th case is also the vice versa. The XNOR operation and XOR operation can be replaced with one another. Okay, so why I have derived these 8 different cases? here, because you can see here the AND operators are replaced with OR operator. Okay, this is only given in the steps, but we have also derived different 8 cases and we have understood the duality principle. I hope you are benefited from this video. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.